So far, in the previous lectures that we have analyzed so far, we assumed that the op-amp is a magical three-terminal device and with a very high gain. Okay, it's almost infinite gain. Now we will start realizing or looking at the op-amp from a practical point of view. At the end, an op-amp is nothing but a multi-stage. It is realized using a multi-stage amplifiers. Okay, so once you realize the op-amp using multi-stage amplifiers, to get high gain, you just cascade stages. That's it. That's the basic rule that we follow in any analog design. So we will not go in depth on how to realize op-amps. That's a separate course on analog IC design. But we will look at how to model those practical effects in the op-amp so that I can use that when I'm analyzing basic op-amp circuits. Okay, so what effects will a finite gain have on the transfer functions? The second thing is op-amp can have a finite limited bandwidth. So then I'll come back to what bandwidth means. Right now, you can just take bandwidth as the maximum frequency until which the gain of the op-amp is very high. After that, the gain of the op-amp will become very low. So what happens when you have that? So how does the analysis change? Or what problems does that create to a designer? Those things are of great importance when we are building op-amp based circuits. So this lecture, I'll briefly take you through the history of op-amps. Okay, we'll look at what were the popular op-amps and the op-amps that you guys use in the labs. I think most of you use MUA 741 op-amps. So that those are called general purpose op-amps. It has been in production for nearly 50 years. We'll see that now. Shown in this picture is one of the first operational amplifier ICs. Okay, and if you open this lid, if you open this metal can, the top lid, it's a very small. You can hold it in your hands. It's a very small op-amp, and the op-amps. I remember I used to talk to this professor, one of the old professors from IIT Madras. So when they also had similar assignments like you guys have in your lab assignments, like you guys have in this course, the size of the op-amp used to be as big as your cell phones. It's slightly smaller than cell phones. That was the size of a single op-amp. Okay, then of course the IC design matured and the size of the op-amp shrunk. Okay, it became smaller and smaller. He used to say when he was actually an undergraduate in 1960s. Okay, so at that time, op-amps itself were first manufactured in 1960s. In 70s, you had monolithic ICs mature. That you heard of the word monolithic IC, meaning in a single silicon wafer, you fabricate multiple transistors. Then you had op-amp size of the op-amp reducing. Now you guys can see, right? So you can hold it within your fingertips. This op-amp is exceedingly small, 8-pin IC, the MUA 741 IC that you guys use in the labs. And so if you see each one of these op-amps, I mean, today it's just a part of history. It's almost like you guys, when you hold an op-amp in your hand, you should understand you're holding a relic. It's a very old part of history now. Okay, so what I'm showing here, this is the first generation op-amp. It's slightly different than what you guys are used to, but this was built in 1960s. If you open this top can, okay, the top lid, this is how it will look like. So this here is your silicon wafer. So I'm not sure if you're able to see the color there. So let me use a different color. So this one shown here, this guy is your silicon wafer. So where your chip is fabricated, the op-amp is fabricated. So this here is the schematic of the op-amp. This is the MUA 741's modified schematic after fixing many problems that customers saw. So usually when you have, like any product, right, you have an idea, you build it, and then you ship it off to customers. Then they encounter problems in production. Then you get the feedback back, and then you change it. It's almost like any software release as well, right? You release a software, get the feedback, and then change it. So this was one of the first generation op-amps. It was built by a guy named Rob Widler. Okay, so he was considered as one of the pioneers of analog integrated circuit design in 1960s. And then what we use, the one you use in the lab, is built around 1970, mid-1972 to be precise. And not much has changed in the architecture of the op-amp. Okay, and that's called as a general purpose op-amp. So I think you guys must by now you must understand the pin outs, right? You know how to read the pin out. Uh, what does each pin correspond to? You know how to read the pins in an op-amp. Okay, so this is something they were manufactured and shipped in production, and it is being used in a wide range of applications. Now, it probably because of ASIC and all that digital proliferation, it has come down a little bit. But even now, if you see, especially when we were students 15, 16 years ago, when we used to have these Apogee festivals and all that. So most of the embedded application engineers, when they want to quickly build some amplifier circuits, they use this op-amps, okay, very commonly. And even now, because these are very cheap right now, the first generation op-amps, which were released in the market, were $300. The first generation op-amps, each op-amp used to cost $300. Then a new revised version within 1960s itself came down to $70. They reduced the cost in the next version itself. Now you can get an op-amp for a few cents, right? I mean, in India, for example, you can get an op-amp for less than, I think, if you buy in bulk, I think you can get it within 50 rupees. I'm not exactly sure, close to that number. You can get an op-amp for that price today. A good quality op-amps. So now the price of the op-amp have fallen down significantly, but this was the price initially in 1960s when the first engineers built these products. And Robert Widler is one of a very famous figure in analog IC design. He famously, because the company for which he built this product, the first op-amp, when he shipped the $70 version, I think he didn't get the desired rise or something, and so he left and joined a rival company and built a better product than that. So he's a very interesting character. Probably someday, when I talk about some interesting circuits, I'll talk about that guy. So this shown here is what we call as a photo micrograph. So it's nothing but a zoomed version of this guy. So, okay, so this is how an op-amp will look like. And these guys are called the leads. What you guys normally connect on the breadboard, these pins. You must have seen this for BJTs as well. If you're any circuit enthusiast, these are called leads. This is what you connect in your breadboard circuits. Okay. Usually we just have to learn all those breadboards. They're all part of history. It's been there for so long. I remember one of the first generation professors, who used to build these analog circuits using breadboards. They would follow very strict rules how a circuit should look like on a breadboard. Okay, not a wire should stick out, and you should choose the right length of the wire so that it's very neatly done. The breadboard should look very neat. You just look at the breadboard and you know what circuit it is. That's how they used to build circuits. But now you walk into any lab, no student, I don't think they take it that seriously. Of course, it's different times have moved, but you should just know it as a part of history, piece of history. So if you see, usually you'll have a silicon, and silicon will then be connected to leads, your leads, right? These leads are the external, this is the connection to your external world. In between, from the silicon chip to the pin, these are called bond wires. Okay, and if you see, this is a microprocessor. I mean, this is an op-amp. This is very simple, right? You can visually see all this very easily. If you take microprocessors, right, they will have thousands of pins. I think if you take the new generation Intel microprocessors, general purpose microprocessors, they will have close to 1,500 pins. And 1,500 pins, it's not even, I mean, you'll have a slightly different packaging. You can't even easily discern all these bond wires there. Of course, it's called ball grid array packaging and all that. So probably someday I'll talk about that. But this, to give you an idea, how if you open up this op-amp, if you open up this black casing, you will internally see a chip, something like this, a silvery silicon chip, and some connections to leads like this. It will be connected to leads using bond wires. Okay, this here is a circuit schematic. Since you guys have done a basic course on ADVD, you can recognize some kind of a differential pair, input pair. So I'm drawing on the white part here. So this is some kind of a differential input pair. And this circuitry is an output. It's called a push-pull output. We will discuss this once you guys are sufficiently equipped with the knowledge. I'll talk about the circuits later. And then there are some high gain amplifier stages in between, common source with Miller feedback and all that. Okay, so Miller capacitor compensation and all that. So I'm just showing you guys on schematic how it looks like. And when you fabricate the chip, if you take a photo micrograph, so this is actually looking at the chip under a microscope. This is how it will look like. the silicon wafer. This here you can see these are all wires. I'm assuming this is a capacitor here. Usually if something is so large, it has to be a capacitor. A long metal plate means it's a capacitor. This is how an IC will look like. Okay, so this graph here, I just quickly took the data over the years and the different Opamp ICs by different companies. And if you see most of the Opamp ICs, these are all general purpose Opamps, meaning you can purchase this Opamp from the market. Like I said, you will even get it you can get this Opamp on Amazon. If you go to Amazon, you will be able to purchase these Opamps for less than 100 rupees. Okay, and you'll get it shipped to your house, or you can go to any electronic shops. You'll get these Opamps. And different companies, the MIUI 741, first it was manufactured by National Semiconductors. I think it was later acquired by Texas Instruments. And the IC that you guys use, MIUI 741, is manufactured in 1972. The first version is in 1972. Okay, and for 50 years we have been using the same one. So you can see how much the progression that in the field is. Okay, I mean, I shouldn't say that's not a good example, but I'm just telling you that a good piece of design, a good piece of engineering can last for so long. Okay, and these are all different. On the graph I've shown on the y-axis the average power consumption. So if you guys measure the power from you have plus minus 15 volt supply, you put an ammeter on the before you feed the 15 volt supply to the op-amp, put an ammeter in between and you record the current. If you record the current, then the current times the voltage will give you the power dissipation. This is the number I'm plotting on the y-axis. I'm just showing that power dissipation is coming down. But if you see, the number of pins is remaining the same. Who uses this op-amps? I mean, you will have sometimes a company may be manufacturing some specific application, some alarm application, and they may need a very quick solution, very quick amplification. So they may put an op-amp, general purpose op-amp, and that might serve their needs. Okay, and those guys might purchase it. And students to perform all those hobbyist experiments, they are the biggest consumers of 741. Okay, and yeah, so those are just to give you an idea. These are something that is done today. A lot of microcontrollers, they give you a lot of analog processing internally in the chip itself. But generally for you guys, for a new student, to learn IC design, to fabricate a chip on your own and then put that chip and package that chip and use that chip in your design is a very painful process. You don't want to do that. Instead, you purchase, this is very cheap. You purchase it in the market and build all the amplifier circuits that you want. Okay, so this graph shows these are all 8-pin ICs by different companies. So say for example, you need a very low noise op-amp. You can't tolerate noise in the op-amp. Then there are flavors. There are different versions sold by companies. Maybe they will be priced a little higher, but you'll get those op-amps in the market. You can purchase it. For comparison, I'm showing you guys how this is the Intel microprocessors that have evolved over. This is from 1970 to 2023. I just plotted it for microprocessors for different years. Okay. Now, if you see, right, you start with 16 pins. Those ICs were initially, the microprocessor ICs were 16 pins. So these were the microprocessors, 8086 microprocessors and microcontrollers that Steve Wozniak, those guys, they were computer hobbies in Stanford. Those guys would know the entire architecture of this because they were very small processors in comparison to what we have today. They are much smaller. So they would have a complete idea of the entire motherboard of a PC. Okay, so the PC hobbyist was a big thing. I heard from my senior professors and friends, engineers who worked around that time. So they were a big thing. Computer hobbies. If you're a very intelligent guy in college, you build computers. So if you see here, right, 8086, which is, I think they teach 8086. It is around 40 pins. I'm assuming 8086 is what they teach in your MUPI microprocessors course. It's 40 pins. Now, if you see the latest microprocessors, something like i9 core, whatever the name, the Raptor and other ICs. So it's 1700 pins. Okay, so that's the way it's changing, the microprocessors. Comparatively, if you look at the Opamp IC, which is one of the best-selling Opamp is this guy. They haven't changed much because the applications are analog. Guys build everything hand-coded, right? It's so you build everything using pen and paper designs and some simulator help and all that. Okay, so today we do have some analog ICs. So for example, you can get Wi-Fi chips. Some companies, Qualcomm would make some Wi-Fi chips. There are some specific Wi-Fi chips which will do some RF and analog stuff. It will come close to 100 pins, 100, 120 pins and so on. Okay. But still the pin count is much smaller. Digital guys will have much higher pins. Okay. So that's a very well-known fact. I'm just comparing these two things for you guys because I'm assuming since you have started lab, you must be using this MUA 741 Opamp. Understand the history. When it was first built, it used to be $770 a piece. Now it's so cheap. When you buy in bulk, you get it for very, very, very low cost today. Okay, for a few cents. So, where do we use this? So that's very briefly about the history of Opamps. Okay, and just to tell you guys, you have been using an Opamp that's been in use for 50 years. So that's what when you're building circuits in your lab, think that that product has been there for 50 years. So usually we say that electronic products depreciate, right? When you purchase an electronic product, usually it depreciates. It's a depreciating asset. You can't claim that I own a piece and then it's going to appreciate over time. But electronic components are depreciating assets. But this guy has lost it for so long. 90 the general purpose of AMP, and that's used by students, electronic hobbies who want to build circuits. So I'll take one example for you guys to give an example where somebody might use a practical op-amp circuit. Say a hobbyist designer is designing an application where he's actually using a microcontroller to do some signal processing. It turns out he has a sensor IC that he has brought. That sensor IC produces a voltage signal whose peak to peak is 10 millivolts. Okay, so guys, this is not history now. I want you to come back to the problem solving mode now. We are looking at the mathematics here. So your guy has to design. It's given that the sensor produces an output whose peak to peak is 10 millivolts and average is 0. So which means you can think that the output of a sensor is a sinusoid which goes 5 millivolts above 0 volts and 5 millivolts below 0 volts. This is the output it produces. Now that guy has an ADC with him. That ADC produces a 10-bit output. Okay. So he needs to convert this 10 millivolt signal into a 10-bit output. Okay. So since you guys have already done digital design, I'll explain some things right now, which should, in case if you have any doubts, you can just quickly ask me. You can just unmute and ask me what's your doubt. I'll explain it now. It's a very interesting thing. When you're dealing with signal processing, you're essentially dealing with numbers, right? When I'm amplifying a signal, when I'm adding offsets or, filtering a signal, all that, you're essentially dealing with numbers. When you're dealing with numbers in the analog domain, you're dealing with real numbers. So let's say I amplify the signal by a factor of 10. I will get a sinusoid which will go 100 millivolts peak to peak. Instead of 10, it will be 100 millivolts peak to peak. So I've just multiplied this by a factor of 10. So I'm dealing with real numbers here. That's what's happening. In the digital world, we often we don't deal with the real numbers, but we deal with the representation of the real numbers. So let me ask you a very simple question. If I have a microprocessor wants to represent all the real numbers between 0 and 1. Okay, all the real numbers between 0 and 1. How many bits do you think you will need to represent these numbers? How many bits will you need to represent real numbers between 0 and 1? So let me give a simpler example if that's not clear. If you want to represent 0, 0.25, 0.5, 0.75, I have 4 numbers here. If I want to represent these 4 numbers, how many bits do you think I need? Minimum number, 2 bits, right? You have 4 numbers, you will just need 2 bits to represent them. So the number of real numbers between 0 and 1 is infinity. So therefore, I will need infinite bits to represent them. Okay, that's not practical. So normally what we do is we do this thing called quantization. Okay, you will divide this interval 0 to 1 into some small finite number of intervals. Okay. Normally, that number of intervals will be 2 power n. If you divide your number space, numbers into 2 power n intervals, then you can represent those numbers using n bits. You can represent, if let's say you divide your interval by x intervals, if you divide your numbers in a certain range into x intervals, then you can represent it using binary representation. You will need at least log x to base 2 number of bits, right? I'm assuming since you have done digital design, they must have told you in number representation. No, it's not pulse code modulation. It is just uh, digital representation itself, right? Number system. When they taught you number systems, they usually start teaching you number systems in digital design, right? Why do they do that? They do that because all the operations that we have been talking about in analog design, right? Integration, subtraction, addition, multiplication. Those are all mathematical operations. You can do those operations in analog domain using all these op-amp based circuits, or you can do them everything using a digital micro, which is what we are doing right now, right? When you make a phone call using your cell phone, all the processing, the filtering, all those things happen in a DSP, digital signal processor. That does all the processing. It even probably does some internal amplification if needed. Okay, it is all done by a microprocessor, a digital device. So I'm telling you that to do that processing, it needs to convert real numbers to digital numbers, binary representation. If you want to do it in digitally, right? Addition, everything we know how to do digital addition using digital bits. So I'm showing that if you need this, if you have to convert this into n intervals, then you need log to base 10. And if you understood this is sufficient. If I divide the number of real numbers in the interval 0 to 1 into 2 power n intervals, then I can represent them using n bits. So in each interval, all the numbers between one interval, so for example, 0 to 1, 0.125, I will call it as 000. From 0.125 to 0.25, I'll call it 001 and so on. Okay. So all the numbers from 0.75 to 1 will become 111. So now you have 8 levels using 3 bits. So I'm saying that the designer wants to convert this 10 millivolt signal to a 10-bit representation. He wants to convert this to a 10-bit representation, meaning his output varies from minus 5 millivolts to plus 5 millivolts. And he has to convert the number of numbers, the signal here between minus 5 and plus 5 to a 10-bit output. Okay, which means in your mind, you should think like I'm dividing this into 2 power 10 intervals, and I'm going to assign 10 bits to each value. That's what I'm doing. But I'm giving you an additional information. The guy has access to an ADC. This ADC can be present in a microprocessor or a microcontroller chip. It can be inside a microcontroller chip also. It turns out that ADC is a 10-bit ADC. Okay. But it needs to operate. You have to feed input signals from 0 to 1. If you feed any real numbers from 0 to 1 to this ADC, if you feed a real number between the interval 0 to 1 to this ADC, then it will convert it to a equivalent 10-bit output. Okay, so if you feed a number 0.125, it will generate 10 bits. So it will first 7 bits will be 0, and the last 3 bits will be 001. So it will convert any number in the interval 0 to 1 to 10 bits. So now think like this. Your problem is this right now. You have a real number that goes from minus 5 millivolts to plus 5 millivolts. Plus 5 millivolts, sorry. I want to convert this interval, minus 5 to plus 5, to 0 to 1. What operations do you think you should do? Think like this. I'm asking you to think like an engineer. You have a signal that goes from minus 5 to plus 5, and you want to convert it, this signal. You can think like this. Think it like a sinusoid. which is going from minus 5 millivolts to plus 5 millivolts. You want to pass it through a circuit, some circuit, okay? It should convert it to a 0 to 1 volt sinusoid. It should convert it to a 0 to 1 volt sinusoid. So what operations do you think you need to do? Think, I mean, see, I have to convert 5 millivolts to 1. I have to convert 5 millivolts to 0 to 1. That's a much larger range. 5 millivolts is what? 0.005 to plus minus 0.05 to plus 0.005. Exactly. So one of you said, I need to do amplification. First, I need to amplify it. So let's take this interval. So if I take this interval minus 5 millivolts to plus 5 millivolts, amplify it first. If I amplify this by a factor of 100, what do I get? I get minus 0.5 to plus 0.5. And then I need to shift, I need to convert this to 0 to 0.0 to 1. What should I do? If I have to convert the numbers, I have a set of numbers which are going from minus 5 to plus 0.5. I need to convert it to 0 to 1. What should I do? Level shift, right? By what? By what should by what value should I level shift it? 0.5, right? That's right, 0.5. So if I add 0.5 to this node, this end will become 0 and this end will become 1. So that's it. I need to do two things here. The first step I need to do is an amplification by a factor of 100. So if I have VI, I need to do 100 VI. So that's my first step that I need to perform. And then I need to add an offset VCM or V offset. Let me call it as V, not the word, some common mode, some DC, VDC. Let's call this as VDC. This has to be equal to 0.5. I mean, it can be any programmable value, but it has to be 0.5. I really don't care about, let me tell you, let's say I say that I don't care about the sign. It can be plus 100 or minus 100. I just need to amplify it first. Okay. All I can do is, even if I inverted, flip the sign here, I can then always, take the digital data and then flip the signs for the digital data. I can give that information to the digital guy, to the microcontroller guy, and he will keep that information in mind. That's it. So now if you see, I have reduced all I need to do. I'm just giving you a simple example. I have a sensor which produces a signal which goes from minus 5 to plus 5 millivolts. I need to convert it to a 10-bit digital output. And I said that you have access to an ADC, which a 10-bit ADC, but unfortunately the ADC operates from 0 to 1 volts. Okay, you have to give inputs that are between 0 and 1 volts. So then your problem becomes, how do I convert this plus minus 5 millivolt signal to a 0 to 1 volt signal? To do that, you need to do two mathematical operations. First, you take this 10 millivolt signal, you take this 10 millivolt signal amplified by 100 times, you will end up getting a 1 volt signal. But the DC value will be at 0. So this will go to plus 0.5 and this will go to minus 0.5. Now all I need to do is, I just need to add a DC of plus 0.5 to this, and I have my signal that I want. So that's what I've shown here. These are the two operations you need, and we can build a circuit something like this. If I put a circuit, let's say this is 100R, and this is R, and I apply VI at this point, and take the output here. And I mean, how do we add it? I can just put a current source, I, and ground this here. Okay. And if you're worried about any practical nature of the circuit, you can always see, this is something left to you, as if you have a lot of freedom. You can always AC couple your input signal and then DC couple this node to VCM, and connect this node to VCM. And you can do all those processing. We'll come back to those processings later. But I'm just illustrating you an example. Forget about current source being ideal or not. I think one of you asked me a question sometime back. Because the common mode node voltage will be at 0, does this create problem for the current source? Yes, it does. But here I'm assuming for analysis purposes that this guy is an ideal current source. If you're worried about the voltage being 0 across the current source, you can always connect this to a negative voltage. I can connect this guy to minus VCM, some common mode voltage, so that the overall voltage across the current source is positive. Okay, so current flows from a higher potential to a lower potential. Is that fine? So you can do this. If you, in case you're worried about current source having 0 volts across it, you can do that. So this is my circuit. So can you guys tell me now for this circuit, what will be the output voltage? If you are to analyze the circuit, you can use superposition and tell me what will be the output voltage. So if you remove the current, assume the current to be 0, then it will be minus 100 VI. Yes, minus 100 VI plus, let's assume this current is ICM, I common mode. So you'll have I common mode into 100 times R. Your current here is going to be I common mode times 100 times R. Okay. So then you can choose your ICM. Once you decide your value of R, you can then choose right value of ICM to get the desired offset values. So I can use this guy to set my VDC and this guy to set the gain independently. The gain is dependent upon the ratio of the resistors, and the absolute value of the resistor will determine the DC offset that you are adding. So let me ask you one small question. What do you think is the current that this op-amp is supplying? If I ask you, what is the current supplied by the op-amp, what will be your answer? What will be the answer? What is the current that this op-amp is carrying, output is supplying? So it's supplying, think like this. You have a current VI by R flowing in this direction. Okay. And that current flows through this resistor, which is VI by R. You also have ICM, which is flowing through this resistor in the opposite direction. So the total current that the output supplies is ICM minus VI by R. So your I naught equals ICM minus VI by R. This here is the total current that this guy supplies. Okay. So I just took an example of a circuit to illustrate you how, if you are going to build some application, an op-amp based circuit, how should you think about it? That's what I've discussed. We'll now come back to the op-amp. So far, I just briefly told you guys the op-amp ICs and the cost of an op-amp IC, when the first op-amp IC was built, just for you guys to be informed about the history of op-amps. Now we'll come to the actual topic. Why did we discuss all that? And why did I take this example to show you how a practical circuit can be built? If you have an op-amp based circuit, so far, we didn't really say that we took an example about the saturating nonlinearities. And we said, okay, there is a limitation on what is the peak voltage you can apply. If I tell you that the output voltage cannot go greater than plus minus VSAT, can you tell me in this circuit, what is the maximum input signal level that I can apply and expect faithful amplification? So what do I mean by faithful amplification? A faithful amplification means that if I apply a sinusoid of a peak voltage V peak, the output should be a scaled version of the sinusoid. Some amplified version times V peak. The output, if I measure the Fourier transform of the output, that should contain no tones. I mean, no frequencies other than the input frequency. That's the definition of a linear time invariant system. An op-amp can be seen as a linear amplifier if the frequencies of the output are equal to or the same as the frequencies in the input. There cannot be any different frequencies. If the op-amp is nonlinear, then you will see some different frequencies as well. But for linear amplification, this condition has to be met. The frequency of the output has to be same as the frequency of the input. Okay, that is step one. The second thing is that what about the frequency? Can I apply any frequency? What happens as I keep increasing the frequency of the sinusoid? Let F in be the input frequency of the sinusoid. Will the op-amp still give me faithful amplification? Meaning I should get perfect R2 minus of R2 by R1 times Vi. This should be holding true no matter what happens. Will this work? Under what conditions will it fail? And most importantly, under what conditions will it work? That conditions under which it will work, the condition under which an op-amp circuit works as desired, is normally what we call as specifications. That will be specifications for the op-amp. Okay, so circuit designers normally keep that in mind and design op-amps. So now, what are the specifications? I mean, what are the conditions under which an op-amp should amplify? So if you take a sinusoid, the question you should ask is that if I keep reducing the magnitude of the sinusoid, if I keep reducing the V peak, I keep approaching zero, will it still give me faithful amplification? The answer is no. At some point, your signal will become so small that it will be buried in noise. It will get buried by random thermal noise. We'll see the sources of noise later. But these resistors, anytime you have lossy components, they will produce random thermal noise. And your signal will get buried. It will become so small that it will be buried in the noise. Okay, so it's like you can picturize like a classroom with everyone talking to each other. Okay, and if you are trying to make a conversation with your friend, and if the whole classroom is talking at a much noise, in a much louder voice, you won't be able to converse after a point if you talk especially in lower voices. Okay, either you have to increase your voice or you should expect others to lower their voice. Okay, if everyone's shouting, then you won't be able to converse with your friend. That's like noise, right? Your voice is getting submerged in noise. So the person sitting closer to you will also not be able to hear anything. So it's similar, same things apply for amplifiers as well. If your input signal becomes so small that noise submerges it, then you can no longer call it an amplifier. It's no longer, if you look at the output, you will not have any meaningful signal. The second thing is the maximum input level. If I keep on increasing Vp to infinity, ideally the ideal op-amp can theory produce infinite output. But we just said there is a limitation that the outputs cannot go. In the previous two lectures, we discussed that the output cannot reach a voltage greater or less than plus minus Vsat. So there is a limitation there. And in fact, engineers often use not just this is the bigger limit. Engineers are more worried about fidelity, meaning if you measure the output frequency, the spectrum of the output signal, that should contain only one frequency. If it contains other frequencies, then you say that your signal is corrupted. Okay, so generally in audio, we use a performance metric called harmonic distortion, total harmonic distortion. Okay, so if you apply a sinusoid of frequency Fin, output will contain 2Fin, 3Fin, 4Fin, and so on. So these are all unwanted signals. And they will distort. If a song will be distorted when you hear to it. Okay, so that's what these amplifiers can also add some nonlinearities. So later we'll see how to fix the nonlinearity problem. So there is a limitation. You can't apply a peak voltage as high as you wish. There is a limitation. After which you can no longer, either your output will not be a faithful amplification of the input, or you will end up getting unnecessary harmonic components. You will get this will start dominating your output, and more than your fin, the input signal's frequency itself. So that determines what is the maximum voltage you can apply. The third one, which I'm discussing those topics which will be very useful for us when we are analyzing circuits. Third one is what we call the maximum frequency of operation. So which is until what input frequency. I'll just start my input frequency from DC and then keep sweeping it. I'll keep on increasing the sinusoid's frequency. So initially low frequency sinusoid and then a high frequency sinusoid. I'll keep on increasing the frequency of the sinusoid and then see if my amplifier is still producing perfect amplification or not. In practice, the op-amp will give you very high gain, or the op-amp will give you very high gain until only a certain range of frequencies. So therefore, your op-amp will behave like an op-amp for a certain range of frequencies. And we call that as UGB. So usually UGB is a metric which tells you what is the maximum frequency you can apply to your op-amp. So when you're performing experiments in your lab, you can verify this. You build a simple, let's say they taught you how to build a inverting amplifier circuit, build this circuit, and then slowly vary. You guys have this function generators. Function generators will give you options to vary frequencies also. So you can vary the frequency of the sine wave. They give you all options. You can change the peak voltages, or you can add DC offsets and all that. So you can actually start from the function generator and increase its frequency slowly. And at some point, plot the waveforms on an oscilloscope at the output and the input, and you will notice that at some point, your output gain will start decreasing. Okay. So then you know that, okay, there is some problem that's happening in the op-amp. So we'll mathematically see what's happening, what is the impact of that, and what design considerations that engineers keep in mind while designing it. So those are important things. Okay. So I'll stop my lecture at this point. I just gave you guys an idea. What are the different problems you will encounter in op-amp and how to design that. The next lecture, we will quantify them. We'll try to quantify them mathematically. Each of these effects. I told you guys, small input, what is the minimum input signal, what is the maximum input signal level, and what is this UGB, the maximum frequency you can apply. There is one other parameter called slew rate for op-amps. We use it mainly for op-amp circuits. And what does that mean? Okay, so that is also a measure of how fast your op-amp reacts. Okay, so we'll talk about those things in the next lecture. Okay, I'll stop at this point.